discussion of kinetic theory of gases. So last time we found relationship between such key thermodynamic parameters as pressure and temperature directly with the average kinetic energy of molecules of ideal gas. In particular, we consider um, single atomic molecule, like just atom. Um, and that's why we consider 3 degrees of freedom, which are associated with the translational motion of these atoms. So today we try to find relationship between microscopic parameters and thermal characteristics, like in particular molar specific heat capacitance of ideal gas at different processes, and consider options which may be possible for diatomic molecule when we have opportunities for rotational and vibrational motion on top of translational motion, which we already considered. So first, let us discuss such 3 processes. Oops, this color should be changed. So we have pressure versus volume. And here we show two, what is going on? How did it happen? Okay. So here we have two isotherms. What does it mean? That any point on this curve corresponds to the same temperature. So it's T1 and T2. So we consider some initial state. Here will be I, initial state. And then we consider 3 different processes. So first process, let's say we consider at constant volume, goes to this, let's say, F1, final state. Then we consider another process at constant pressure. It will be F2. And some process, some adiabatic process, it will be some F3. We will come to this. So first question. We see that these processes are quite different, but in terms of, in the scope of first law of thermodynamics, which change of which parameter will be the same for all these 3 processes? So what first law of thermodynamics tells us? Can you recall me? That is based on this principle, but to be more specific, it tells that change of internal energy is equal to heat plus water. So work done. So you claim that work done by all these 3 processes will be the same. That is not. Okay, that's not what you wanted to tell, because if we consider specifically the first process when volume is constant, then work is equal to 0. Work is not done. And work, as we defined earlier, will be negative integral from initial to final volume of P times dV. And of course, if volume doesn't change, it will be equal to 0. So actually, this area under this curve, which describes the process. So here will be 0, here will be 1, value here will be different value. So work is not the same, but change of internal energies will be the same, because no matter how we go, which direction, we go from one isothermal curve to another isothermal curve. For all these final points, they are all at the same isothermal curve, means temperature, final temperature will be the same for all these processes. And initial was obviously the same because we started at the same point here. That means that if temperature is the same, then internal energy will also, change of internal energy for all these processes will also be the same. So this is one of the key moments which we need to remember as we go further with our derivations. So since these processes are different, they result in the same change of internal energy, but in terms of amount of heat and work done and heat transferred, they are different. So let us consider, first of all, two processes which are of our interest. So this first at constant volume and at constant pressure, and introduce heat via molar specific heat capacitance at constant volume and at constant pressure for ideal gas. So in the first process, when we have constant volume, we can write that heat is equal to, let's denote nu with nu the number of moles, times CV times delta T. So CV stands here for specific molar heat capacitance of ideal gas at V constant for isovolumetric process. So in order to get amount of heat, we need to multiply this CV by number of moles and by change of temperature. Or in other words, CV is amount of energy needed to be transferred to the system or heat in order to change its temperature by 1 Kelvin if the system consists of 1 mole. And for the other process, we can write nu times Cp times delta T at P equals constant. So the question now will be, are these Cp and Cv the same or they're different? And if they're different, what is larger or what is small? So before we go for any derivation, let us turn on some logical thinking and figure out what is what. They are different, that's for sure, otherwise we would not define them differently. That's quite logical statement. Now let us consider which one is smaller, which one is larger. What do you think about this? CV is larger. CV is larger. So what do you put behind this statement? So if we increase the volume, pressure will decrease. Wait, but CV stands for specific molar heat capacitance at constant volume. Yeah, so with so the pressure is changing and it's easier to heat to change the energy. More energy is needed to heat the substance. Okay, that raises its temperature by 1. For which process? So that is correct start, but we need to also correctly finish this state. For which process we need more heat in order to change its temperature by 1 Kelvin? For constant pressure. For constant pressure. And the reason for that is that when we keep constant pressure and start to provide certain heat to this system, this heat will be redistributed. Part of it will go to increase of internal energy, and part will go to perform work by this system. In the second process, when we have constant volume or CV, all energy which we transfer in the form of heat will go to increase of internal energy because work is not done. In that case, since we consider processes with the same change of temperature and the same change of internal energy, it will require more heat to be transferred in order to increase temperature from T1 to T2 for process with constant pressure. And with constant volume, obviously, we will require less. So it means that Cp will be larger than Cv. How much larger, we still don't know, but that we can consider in more detail now. So from last discussion, we found that internal energy of ideal gas will be equal to total kinetic energy of ideal gas, like all atoms. And that can be represented if we assume a single atomic case, and as, as a reason of this fact, we consider 3 degrees of freedom. So that will be 3 second times n, number of atoms, times kb times t. Or we have shown that that will be 3 over half, 3 half times new number of moles times r times t. So we have shown this previously. Now for V equals constant, so isovolumetric process, we can write that work defined as minus integral V initial to V final P times dV will be equal to 0, and change of internal energy will be equal, you're welcome, to amount of heat transferred to the system, Q. So in this case, we can write that delta E internal will be equal to nu times Cv times delta T. um, from here, we write that Cv will be equal to 1 over nu amount of moles times first derivative of internal energy over temperature. Here we can substitute this expression for internal energy. So this will be 1 over nu times d, here 3 half nu times RT over dt. And that will be equal to 1 over nu 3 half nu r dt, because these guys are constants, over dt. We cancel out nu, cancel out dt, and end up with 3 half times r. So for monoatomic ideal gas, molar specific heat capacitance at the constant volume process, when isobaric process, volumetric process, Cv will be equal to 3 half times R, or we can even give the numerical value that will be 12.5 joule per mole per Kelvin. So that is molar specific heat capacitance at constant volume. So we have shown in our discussion that um, this is smaller than specific molar heat capacitance at constant pressure. So let us show also quantitatively how much smaller it is. So we consider pressure constant now. And for that, change of internal energy will be equal to the sum of Q times W, heat and work. So that can be expressed as nu times Cp already times delta T and plus minus P times dV, which stands for work. Uh, for the left side of this equation, we can write that delta E internal is equal, we already defined it previously, it can be expressed as nu times Cv times delta T. So why we can use this? Because we know that both of these processes are happening between two isothermals, and change of internal energy for both isothermal and isovolumetric and isobaric processes will be the same. So no matter how we express it, we can we will get the same number. So for left side, we can write nu times Cv delta T, and that will be equal to this part. So let us write it down. So we have it nu times Cv times delta T is equal to nu times Cp times delta T plus minus P times delta V. So we want this part also be expressed in terms of change of temperature, because we have here and here change of temperature. So how we can do that? We can recall the equation for the state of ideal gas. PV is equal to nu times RT, and that's why we can write that P times delta V should be equal to nu times R delta T. So now we can substitute it here, and we get nu times Cv times delta T. That is equal to nu times Cp times delta T plus, well, actually, we can already open this parenthesis, get minus. So that will be nu times R times delta T. Now what we see here, we can cancel out this amount of moles. We can cancel out temperature, and we end up with the following equation. Cv is equal to Cp minus R. Or in other form, we can express Cp, which we are looking for now, and that will be equal to Cv plus R. Um, that is 3-second R plus R will give us 5-second R. So that is specific molar heat capacitance of ideal gas at isobaric process. And indeed, as you see, Cp is larger than Cv. Another important parameter, which is used quite often specifically in adiabatic process, which we will consider next, is the ratio between Cp and Cv. So gamma is equal to Cp over Cv. So that is like adiabatic coefficient, so-called gamma. And for single atomic ideal gas, that will be 5 over 3, and that will be something like 167. So now we still have this adiabatic process, which we considered initially. So we have isobaric, isochoric, and adiabatic process. So let us consider in more details adiabatic process because it is a bit different, like special case. When what is the definition of adiabatic process? We already did that, like gave the definition. Uh, what is special about adiabatic process? So isothermal process, constant temperature, isochoric process, constant volume, isobaric process, constant pressure, and adiabatic process, there is no heat transfer between system and environment. So that's a special feature of adiabatic process. Okay, so we keep that in mind, and in this case, we can write that for first law of thermodynamics, change of internal energy is equal to Q plus W, and Q is equal to 0. So in this case, we also can write the change of internal energy is equal to nu times CV times delta T. Because again, change of internal energy for all three processes we should consider will be the same because they are happening between two isotherms. So in this case, we can write that small change of internal energy, dE internal, will be equal to nu times CV times dt, and that should be equal to minus P times dV, means work done by the system. Change of internal energy is happening, we are performing some work by system. Um, Now let us rearrange this in such a way which will help us to get the differential equation to describe relationship between pressure and volume in adiabatic process. So what we need to do? From here, we can express dt. dt will be equal to minus p times dv divided by nu times cv, and another thing what we need to do, we need to take the differential of state equation of ideal gas. So again, we recall it, it's PV equals to nu times RT. Um, these guys are constants, nu and R, they are constants. We don't change amount of moles, and R is constant by definition. So that's why if we consider dPV and here dVRT, we will get the following. It will be kind of taking derivative of a product of two functions. So it will be P times dV plus V times dP, and that will be equal to nu times R, because they are constants, we don't care about them, we just factor them out from differential, and here will be dt. So we have this equation, and now we need to make it special for adiabatic process. And for that, we substitute this definition of small change of temperature in this equation here. So what we get? We have P times dV plus V times dP. That is equal to nu times R. And here we have minus P times dV over nu times CV. We can cancel out this guy, and eventually we will get minus R over CV times P dV. Okay, now we divide left and right side by product P times V. Let's see what we get. First term in the left will give us dV over V. Second term will give us dP over P. And in the right side, we get minus R over CV. And here will be dV over V. Now, next step, let us recall what we derived for CP and CV. CV, or maybe like CP, specific molar heat capacitance at constant uh, pressure, is equal to CV plus R. From here, we can write that R, universal gas constant, is equal to Cp minus Cv. And now we can substitute it here. So let us do it. And we have dV over V plus dP over P. That is equal to minus, here will be Cp minus Cv instead of R in the numerator, and denominator we have Cv. And that is multiplied by dV over V. If we recall this gamma coefficient, that is ratio between Cp and Cv, so we can proceed here with minus. That will be gamma minus unity times dV over V. Now let us transfer right side to the left. So we set it to 0, the right side. Get dV over V plus dP over P plus gamma minus unity dV over V. And this is equal to 0. So now we can cancel out this and this. And eventually we get dP over P plus gamma times dV over V. And that is equal to 0. So this is our differential equation we were looking for. Now, when we integrate this, we get the following. It will be natural logarithm of pressure plus gamma times natural logarithm of volume. And that should be equal to some constant. So we don't define constant here. It's not what we want to do. We just need to find the relationship between pressure and volume. In other form, we can write that pressure times volume in power gamma is equal to constant. That is the relationship between pressure and volume in adiabatic process. As you recall few lectures ago, we discussed how pressure and volume depends on each other in isothermal process, and that was for isothermal process, that was P times V is equal to constant. So where this power was unity. Since gamma, which is equal to Cp over Cv, is larger than unity because Cp is larger than Cv, adiabatic process will be depicted in this PV coordinates as steeper process. So if we come back here for our plot, we see that this adiabatic process is steeper than isothermal process because of gamma, because V in power of gamma and gamma is larger than unity, which we have for isothermal process. Similar, we can write also for relationship between temperature and volume, which are also changing in adiabatic process. So that will be T times V in the power gamma minus unity is equal to constant. So these two relationships um, are valid for adiabatic process and can be used when we deal with them. So now we considered all three processes which we highlighted at the beginning between two isothermal curves, means with the same change of internal energy. Um, and the next step, we need to talk about so-called equipartition of energy. Means we need to discuss options for additional degrees of freedom when we have diatomic molecule of ideal gas. So far, we only have considered only single atomic ideal gas, but it's possible that it's not a single atomic case. So we have two atoms in a molecule. So let us consider this. So we have some system of coordinates. This will be x, y, and z. And let me pick up another color. We have a two atomic molecule. So it can move along all these axes. So it can perform translational motion. Uh, that will correspond to this original three degrees of freedom, which we had for single atomic ideal gas case. However, besides that, it can also rotate about this axis. In this case, we will get two more degrees of freedom. So rotational motion plus translational will possess 5 degrees of freedom. And one more option, we have some chemical bond, obviously, between these two atoms. And at some conditions, we can disturb it, so it starts to vibrate. And that obviously will bring another contribution to kinetic energy, because we know from mechanics that translational, rotational, and vibrational motion, they all possess some kinetic energy, and total kinetic energy will be defined by contribution from all of these motions. And in this case, they also will define total internal energy of ideal gas. So this will also add another 2 degrees of freedom to the ideal gas. So for instance, if we consider translational and rotational motion of the atomic molecule of ideal gas, then internal energy can be expressed as 3 times n, means n total number of these molecules, times 1/2 kBt. That we have shown previously, that this stands for one single degree of freedom contribution into the average kinetic energy of a molecule. And then we need to, so this comes from um, translational motion, then we need to get 2n times 1/2 kBt. That is another contribution from rotational motion. So in total, we will get 5/2 n times kBt, or it will be 5/2 nu RT. So now we have kinetic internal energy um, defined by this equation. So when we derive value for Cv, which is specific molar heat capacitance of ideal gas, at constant pressure, constant volume, will be equal to 1 nu times dE internal over dt by definition. And here we will get 1 over nu d over dt. And here we have 5 half nu times RT. So this will give us 5 half times R. So we see that as opposite to single atomic case, when we had only translational motion and 3 degrees of freedom, uh, in that case Cv was equal to 3 half R. Here it is higher. Because why it's higher? Because when we provide certain uh, heat from outside to the system, we need to not only spend this heat to increase translational motion, but also need to initiate this rotational motion. So it requires more energy. So with uh, this, we can write also for Cp in the case of the atomic molecule when we consider rotational motion. That will be still valid, this equation which we derived, Cv plus R, but since Cv now is larger, it's 5 half R plus R, that will be 7 half R. So you may ask me, what value should we consider now? Because is it always for the atomic molecule Cv is equal to 5 half over 5 half times R, or not? Plus we have also vibrational, which we can consider a little bit later. The thing is that it really depends on temperature. So in order to get some contribution from rotational motion, we need to activate this motion. And we have at any temperature larger than 0 Kelvin, we have always translational motion. However, it requires certain temperature in order to thermally activate the rotational motion. And that is also valid for vibrational. That is even more difficult to excite. So it happens only at very high temperatures. So that's why it will change with some steps as a function of temperature. We will consider it a little bit later, but now if we add on top of translational and rotational also vibrational, that will bring another 2 degrees of freedom. And for Cv, we can write that it will be already equal to 7 half R, and obviously Cp will be equal to 7 half R plus R. Can write it here. Cp will be equal to 7 half R plus R. That's when we have also vibrational motion on top. So let's say, can say translational plus rotational plus vibration. So now we consider Cv as a function of temperature, because as I mentioned, it will not be always the same. It will depend on temperature of ideal gas. So let's say here we have Cv, here we have temperature in Kelvin, here is Cv. So we can consider 3 possible values. They cannot change, they cannot possess any different values besides this which we define. So this is 3 half R, 5 half R, and 7 half R. And now we have here some logarithmic scale for temperature. So this will be 10 Kelvin, here will be 100, like here will be something like 1000, and higher temperature. So let me change the color of our pen. And at low temperature, up to something like 100 Kelvin, um, any type of motion besides um, translational will not be activated. So thermal temperature is too low. And that's why that regardless the fact that this ideal gas is diatomic, not single atomic, we still deal with its molar heat capacitance defined only by translational motion, and that is 3/2 times R. If temperature goes higher than 100 Kelvin, then we have a transition to this second level when contribution from rotational motion is already thermally activated. So in this temperature range, we should take into account both translational and rotational. Obviously, that makes us to go to increase degrees of freedom from from 3 to 5. And smaller specific heat capacitance at constant volume will be defined now as 5/2 times R. Then if we go even higher, like above 1000 degrees, then we have a transition to next level when we already excite this bond, chemical bond between two atoms, and two atoms start to vibrate with respect to each other. So in that case, vibrational motion also should be taken into account, and this value of this is the value of CV. The thing is that usually we do not operate at this extremely high temperatures because that is like 2 and higher Celsius of Kelvin. We do not have such usually conditions because even it's difficult to handle such gas in some volume, which walls will um, deal with such high temperature. And usually it's actually whole field of study, like vibrational spectroscopy, in order to figure out what is chemical composition of your gas you deal with. There's an option to excite this vibrational motion of molecules with some light, some photons. They bring enough energy to excite this vibration, and then we can see at which valence this gas absorbs light, um, which can excite this vibration. Based on the energy which is needed to excite this vibration, we can determine what kind of chemical bond we deal with, and that tells us what type of material, like this gas, is this sample. So that is vibrational spectroscopy, and usually uh, thermally, it's not this vibrational motion is not excited because it requires extremely high temperature. So usually we work in this range when the atomic ideal gas, for instance, will possess either 3/2 R or 5/2 R if we already add on top of translational motion rotational motion of these molecules. If we have more atoms in molecule, and that's obviously possible scenario because the atomic molecule is the simplest molecule which can be, then there are obviously more complicated cases for calculation of this specific molar heat capacitance because complex structure of the molecule results even in more degrees of freedom for rotational and vibrational motion. So let us summarize our discussion today. We considered three important thermodynamic processes, which are isobaric, isochoric, and adiabatic. But specific condition when they happen between two isothermal curves. Means that change of temperature is the same for all of these processes, and change of internal energy obviously also the same. So we introduce the concept of specific molar heat capacitance of ideal gas at constant pressure and constant volume. We derive equations for this specific molar heat capacitance, initially for translational motion only for 3 degrees of freedom, have shown that indeed CV is larger, CP is larger than CV. And that is because in the case of isobaric process, we need more energy to change temperature of the system by 1 Kelvin than we require for isobaric or isovolumetric process, because their work is not done and all provided heat is used to increase internal energy. So we also considered adiabatic process, where we found the relationship between pressure and volume for adiabatic process. It is like P times V to the power of gamma. Gamma is the ratio between Cp and Cv. It's always larger than unity because Cp is larger than Cv. And that's why when we plot this process, adiabatic process in PV system of coordinates, it looks steeper than isothermal process. Because for isothermal process, we just have P times V equals constant. And we considered additional contributions from additional degrees of freedom for diatomic molecule of ideal gas, when it's possible to consider on top of translational also rotational and vibrational motion. And what is important, that not always all of these three motions are happening, because rotational and vibrational motion, they require thermal activation. So that's why usually vibrational motion is not the case, because it requires extremely high temperatures. So it can be excited by absorbing some photons of specific energy, which is required to excite this specific chemical bond between two atoms. Usually we deal either with translational motion of the atomic molecules at low temperatures, and at higher temperatures already rotational motion is excited also and possible. So CV increases from 3.5 R to 5.5 R. With this, we finish our discussion for today, and we will continue considering thermodynamics next week. Also, we're coming closer to introducing second law of thermodynamics, but until then, I wish you good weekend and have a good evening. Thank you very much for your attention.